Okay. All right, let's begin. So this is the last in our series of lectures on convolutional neural networks. Anybody remember what the last topic that we were discussing was? What was the last thing we were discussing? Anybody? So come on, guys. Backprop. We were specifically discussing just backprop, was it? What was it we were discussing? Convolutional backprop. We were discussing how backprop can be applied through convolutional layers and also through pooling layers. So here is a quick recap. This is what we're going to do today. We're going to go through, complete the business on backprop. I'll do a quick recap first and talk about some additional final topics. So what we've seen so far is that shift invariant pattern classification, such as does this picture contain a cat or does this recording contain the word hello, are best performed by scanning for the target pattern using CNNs or TDNNs. But these are actually shared parameter models, and so you have to account for this sharing of parameters when you use backpropagation to train them. And so here's the entire setup. As in your standard training, when you want to train the model, you're going to use gradient descent. Gradient descent needs computation of gradients, which means that for each training instance, we need to know how much perturbing any parameter will change the divergence between the output actual and desired outputs of the network. So for each training instance, there's first a forward pass where you pass the instance through the network. You compute an output, you compute the divergence between the output and the desired output, and pass the derivatives backward. Now, you would have regular backpropagation like MLPs until the first layer of this MLP, and then the derivatives at the input to this final MLP will be folded back into the shape of channels, and then subsequently we'd have modified backpropagation rules from here to compute the derivatives going backwards. And when we modify these derivative rules, we have to deal with the shared computation and convolution layers, and we have to deal with the pooling layers. So the two key components of backprop were that for convolution layers, given the derivatives for the output activation map, we had to figure out how to compute the derivatives with respect to the affine map. And then given the derivatives for the affine map, we had to figure out how to compute the derivatives for both the filters that were used to compute the affine map and the previous layer channels. For the pooling layers, given the derivatives of the output of the pooling, we had to figure out how to compute the derivatives at the input of the pooling. Now, for the convolution layers, transferring derivatives from the activation to the affine terms was fairly straightforward. The activation map was obtained by applying an activation function pointwise to all of the elements of the affine map. So each y was basically obtained by applying an activation f to the corresponding z, where z represents the affine terms and y represents the output of the activations. So when you're performing backpropagation, we will assume that we have the derivative of the divergence with respect to the elements of the y's. Then the derivatives with respect to the y's must be transferred back to obtain derivatives with respect to the z's. And just applying the chain rule over here told us that we could do this element wise. The derivative for each element of z was obtained simply by multiplying the derivative for the corresponding element of y by the derivative of the activation function that was applied to z to compute the y. So this was how we computed the derivatives for z's from the derivatives for y's. Now this is straightforward. The more complex operation was how you transferred these derivatives back to compute the derivatives for the filters and the derivatives for the previous layer channels. And here again, We saw that when we went through the math and we boiled the whole thing down, the operation was very straightforward. If you want to compute the derivatives for the mth channel of any layer, then you would pick up the mth channel of all of the filters, and these two would be used, this mth channel of the filters would be used in conjunction with the derivatives for the affine maps that resulted from the filtering to compute the derivative for the mth channel of the input. Now, why we needed to pick the mth channel of the filters? Was this clear to you guys? Can somebody tell me why we picked the mth channel of the filters? Anyone? Any responses? Or oh, wait. So why do we pick the mth channel of the filters? Can you guys hear me at all? Is there...
It's because that's the only channel that interacts with the mth channel of the input.
So the mth channel of the filters is the only channel of the filters that interacts with the mth channel of the input. And so these are the only ones that we would need to consider, right? What did we do with these things? Can somebody tell me? What did we do with the mth channel of the filters? Anyone? Some? Is that what we did? What did we do? Anybody else? I'm assuming you are paying attention. We were computing the derivatives of the mth channel of the filters. What did we do? Anybody else? Someone want to give me a correct answer? Flip them, then convolve them with the derivatives, right? So you flip these guys and you convolve them with what? What did we convolve the flipped filters with? Anyone? Input? Input? This is the input. Did we convolve the flipped filters with this guy? We convolve the flipped filters with the derivative for the z's, right? So here's what we did. We took the... Now see something interesting. The filters, if I arrange them, look like so, right? It's actually a three-dimensional tensor because each filter is... It's actually, interestingly enough, if you look at the entire bank of filters, the bank of filters is a four-dimensional tensor. Why is the bank of filters collectively a four-dimensional tensor? Anybody? You want to tell me that? I have not told you this. I'm asking you to guess. Why is the bank of filters a four-dimensional filter tensor? Anyone? Somebody want to guess? Can I just pick a random name and ask you? Batch size? Anything else? Okay, so look, each filter, what is the shape of a single filter? Anyone? What is the shape of a single filter? Is it 2D? It's 3D. A filter has, the filter face has two dimensions, but it has many channels, right? So each filter is a three-dimensional tube, a three-dimensional rectangle, a hypercube, right? But then you have D of, several of these filters. So collectively, if you think of these cuboids stacked together, it actually ends up being a four-dimensional tensor. Now, what is the, so if I flip the four-dimensional tensor, if I transpose the four-dimensional tensor, what would happen? Now this, within this arrangement, rows and columns would get transposed, but within each of these guys also, the rows and columns would get transposed. So transposing the entire operation and this entire four-dimensional filter and picking one element from it would mean that first, instead of picking this column, I'm picking the row, and then within the row, I'm flipping each channel across the diagonal. So it's transposed in every possible way. Did that make sense to you guys? How when I think of this as a four-dimensional object, then picking the mth row and then transposing the mth row, flipping it left to right, top to bottom, is like transposing the entire four-dimensional cuboid and then picking one 3D cuboid from it. That makes sense? Yes, no? So, okay. I just see like three S's, so I seem to have lost the rest of you guys. Okay. And so that means that basically what we are doing is that we are transposing the entire filter and then convolving the zero padded derivative maps with the transposed filter to get the derivatives for the collection of input channels. That's why this derivative computation is often also called a transpose convolution. That makes sense? Yes, no? Okay. So, but mechanically speaking, what we did was we picked up the M throw, made a filter of it, flipped each channel of it, and you're going to have as many channels as output channels. So you're convolving that with the collection of derivative maps, right? So this was how we computed derivatives for the Y. How did we compute the derivatives for the filters? Now, if I want to compute the derivative for the nth channel of any for the nth channel of the filter, then the filter, or for n, say the first channel of the filter, nth filter. Now the nth filter only computed the nth output map. So we picked up the nth output map, the derivative map for the nth output, and we convolved that with the first input channel to get the derivatives for the first channel of the nth filter. So if you convolve this guy, the derivative map for the nth output channel with every input channel, you're going to end up computing the derivatives for every channel of the nth filter. So for the nth filter, you pick up the nth output map because that's all the filter computes, and then convolve its derivatives with all of the inputs, and you get the derivatives for all of the filter terms. Okay. So are you guys with me so far? Yes, no? Oh, okay, this is all just old hat, right? So we've gone through how to compute derivatives for the convolution and how to compute the derivatives for the activations and how to compute derivatives for the convolution. So this is done. The next thing that we went over is derivatives for pooling layers. And again, in the pooling layer, if you were performing max pooling, we just saw pooling pools groups of values to reduce data sensitivity, and the most common pooling is max pooling. So when you perform max pooling, you just find out the index of the largest element and copy the value over, right? And you keep doing this going left to right, top to bottom. And so when we computed the derivatives going backwards, we realized that it was only the largest value that influenced the output. So we just copied the derivative at each point over to the element that actually that had actually been copied over at that location. So here 6 came from the bottom left corner of the window. So the derivative at the location of 6 is copied over to the bottom left corner of the window. The rest have zero derivative because they don't influence the output. Now, so when we saw this in terms of code, here's what we saw. When you're performing the forward operation, you have, as you scan the inputs, you do this channel by channel. At each location, you found the index of the largest element and copied the value of that index over to the output. So when you go backwards, you just copy this yxy, the derivative at yxy, over to the derivative at the location from which the y itself was obtained. So the back propagation rules for max pooling were very simple. The other operation we saw was mean pooling. So for mean pooling, you were given a window of inputs. You computed the average. So when you go backwards, basically what this means is that this one is each element, the sum of all 4 elements divided by the number of elements in the window, 1 over k squared, times the sum of all the elements. So this derivative basically is going to be distributed over all k-squared elements in proportion. So you just copy this derivative, divide it by k squared. In this case, k squared is 4. And so 1 over k squared of this derivative gets distributed to all all the elements within the analysis, within the window that contributed to the mean pooling. So once again, if you were looking at this in terms of code, you do this channel-wise mean pooling. You would scan, and at each location you computed the mean of the elements within a window. So going backwards, all you did was you redistributed the derivative divided by the size of the window itself over all of the elements that contributed to that particular element. So this was just a very simple mean back propagation operation for mean pooling. But then what does it mean? If you actually look at it, there's a plus equal to, right? So it turns out that in the case of mean pooling is just a convolution operation, right? Mean pooling is like saying, I'm doing this channel wise, and within each channel, I'm convolving the input with a filter where all the values of the filter are 1 over k squared. So going backwards is going to give you the same kind of back propagation operation that we had for convolution, except it's channel wise. So you would be zero padding your derivative map for the output of the mean pooling to make sure that where the number of rows and columns of zeros that you pad is going to be the number or the size of this pooling window minus 1, and then this zero padded derivative map is going to be convolved with the uniform filter to get you the derivatives of the input to the mean pooling. Did this make sense? How the backprop for mean pooling is also convolution. Yes or no, guys? I see like 2 yeses. Okay, so this is straightforward, right? And so we've dealt with mean pooling layers. There's one more kind of operation that we spoke of, for which we have not discussed the back propagation rules. What was that operation? Anyone? We spoke of a different operation also. Resampling, right? Upsampling and downsampling. We have not discussed this, but before that, let me actually release the first poll. There are 2 questions here. I'm assuming you guys can see the poll. So, okay, 5 seconds, guys. And the poll. Okay. Stop sharing, go back. Okay, what is the answer to the first one? True or false? Second one? Also true, right? So when backpropagating through a max pooling layer, derivatives from the pooled output backpropagate only to the position of the largest input within the input pooling window. When you backpropagate through a mean pooling layer, derivatives are distributed uniformly over the input pooling window for that output, right? And so we've gone through the key components, but then we left out resampling layers. Upsampling and downsampling layers can increase or decrease the size of the map. So upsampling followed by, and we saw that upsampling followed by convolution can be viewed as convolution with a fractional stride, and convolution followed by downsampling can be viewed as convolution with a stride greater than 1. Again, the key thing is we combined upsampling with the convolution that came after it when we called it convolution with a fractional stride. On the other hand, we combined downsampling with the operation that came before it by calling it convolution or pooling with a stride greater than 1, right? So how do we backpropagate through upsampling and downsampling layers? Now, here's what the downsampling layer was. If I had some input and I wanted to say downsample it by a factor of 2, I would first zero out every second column and every second row, and then just copy over the remaining elements. So now, these elements which have been zeroed out, do they have any influence on the final output of the network? The elements that have been blacked out, right? So what is the derivative of the loss with respect to these elements? They don't influence the output at all, right? You can change, and they're constant. They're being ignored. It doesn't matter what the value was over here. Changing this value by a massive amount will have absolutely zero effect on the output. So now we mentioned something very important with respect to the size of derivatives, right? What was that we mentioned about the size of derivatives? If I have, say, an n squared operation going in, n squared input going into some operation, and the output is some size, and then I compute the loss from that output. When I go back, what is the size of the derivative going to be? Anybody? What did we mention about the size of the derivative? We mentioned this. This was very important, right? It didn't matter what the size of the derivative was. It can be small, it can be large, I don't care. This input goes into some operation, whatever this operation might be. It doesn't matter, right? And then out comes a value. In our case, the final value is a scalar, which is a loss. So then when you compute the derivative of the loss with respect to this input, the principle says that every one of these elements effectively influences the loss. The influence may be zero, but the point is for every one of the elements in the input, there is a derivative. There is a derivative of the loss with respect to that element, which means that when you compute the derivatives going backward through any operation for the derivative for the loss, the size of the derivative is going to be the same as the size of the input itself. In reality, it's actually going to be the same as the size of the input transposed. For the gradient, you transpose the derivative back, right? So the size of the gradient, which again is the transpose of the derivative, right, is always going to be the same as the size of the input itself. That makes sense to all of you guys? Yes, no? Right. Okay, so now I took this input and I downsampled it and I made it smaller. Then when I compute the derivative going backwards, what is the size of the gradient over here? What will the size of the gradient be? Anyone? What will the size of the gradient be, right? So what is W over K? I'm not clear what you mean by W over K. So let's say this is n cross n, right? If I can get my pencil. So let's say this input is n cross n. And then I downsample by a factor k. So this is going to be size n over k cross n over k, right? Then when I go back here, what is the size of this derivative? When I compute the derivative at the input to the downsampling, what will it be? Anybody? It's going to be n cross n. It's going to be the same as the input, right? So that's what I'm saying. Not the gradient, not the derivative, but still. The point is the size of the gradient is going to be the same as the size of the input to the net operation. But then over here, we had only n over k cross n over k elements, right? So what happens? Suppose I'm computing the derivative going backwards. I know the size of the gradient over here. It's going to be n cross n. So the very first thing I would do is what I'm really computing is the derivative of the loss with respect to every element over here. And so I'm going to allocate a map, the size of the input itself that was downsampled. This is how much the size of the derivative is going to be, right? Now, over here, what can you tell me about the derivatives for if I'm downsampling by a factor of 2? What can you tell me about the derivatives of for every second column and every second row? What can you tell me about their derivatives? They are 0. These guys, all of these elements had no influence on the output, right? So their derivatives are going to be 0, right? Now the downsample output was simply copied these 9 elements. So what do you think the derivative here is going to be? Anybody? What is the derivative of the top left corner? What is that going to be? 1? What is it going to be? This derivative is going to be the same as this guy. This value and this value are the same value, right? So I can just copy this derivative right over here. I can copy this one right over here because the downsampling copied values. It didn't transform them at all, right? Yes or no? That makes sense to you guys? Right. The remaining values are identical in the original and downsampled map and the forward maps pass. So the derivatives too are going to be identical. So you just copy the derivatives for the output over to the appropriate location of the input. That's it. So this is the backward pass through the downsampling layer. What does this operation look like? Anyone? What does this operation look like going back? What have I done? I've just upsampled. I've introduced rows and columns of zeros between the derivatives. And so the backward pass for downsampling is upsampling. Okay. So here's a pseudocode. I'd just be allocating zeros the size of the input, and then I just copy elements over. That's it when I'm performing back propagation through downsampling. Now for the upsampling, what did we do? In the case of the upsampling, so we know how to perform backprop through downsampling. Let's consider upsampling. For the upsampling, I took my original map and I just inserted a bunch of zeros, rows of zeros and columns of zeros, correct? So once I insert it, I have a larger map. But is there any element over here that actually had a real influence on these guys? Is there any element on the input that had any influence on the shaded guys, right? So when I'm going back, will the derivatives in these shaded locations have any influence on the derivatives over here? No, because there's nothing in the input that actually influenced those guys. Those were just arbitrarily set to 0 in the forward pass. And so for the upsampling layer, given the derivative of the divergence with respect to the elements of the output of the upsampling, you want to compute the derivatives with respect to every element of the input. Now, again, what will the size of the gradient of the loss with respect to the input to the upsampling be? What will the size be? Anyone? What will the size be? It's going to be the same as the input, right? And so here's what we are going to do. We know that these 0 elements were introduced in the forward pass. They are not functions of the input. They're just always introduced as 0 regardless of the input. So during backprop, there's nothing over here that influences these guys, right? On the other hand, these elements were copied over to these locations. So what do you think we do when we backpropagate through an upsampling layer? Anybody? What do you think we do? What do? We just have to copy these elements over, right? This element was copied directly here, so the derivative over here is going to be copied directly here. This one was copied directly here. This element will be copied directly here. And so simply copy the derivatives for the varied locations back over to the input. So backprop through upsampling is basically just kind of downsampling. Now, so here's the thing. Convolution is when you want to downsample during convolution. You actually typically perform convolution with a stride greater than 1 to result in a smaller output map. You don't perform convolution and then perform downsampling. But then if you try to figure out the derivative rules for convolution with a stride, you will quickly find that this becomes quite ugly because you have to deal with different elements differently, right? In this case, it's much more convenient to think of convolution with a stride greater than 1 as a conventional convolution with a stride of 1 followed by downsampling. And once you think of it in this manner, we know exactly how to backpropagate through downsampling. It is trivial, right? We also know how exactly to backpropagate through a regular convolution. That is also a very trivial operation. And so this one now actually becomes very simple, whereas having to deal with this can be quite annoying. That makes sense? And the two are identical. Did that make sense? Yes or no? Right? So you don't need to worry about how do backpropagation rules change when the stride is greater than 1. So what will happen here is backpropagation will first propagate derivatives through the downsampling layer and then through the convolution layer, right? Simpler than modifying backprop rules to account for stride in convolution. Now, this is for downsampling, right? When you have convolution with a fractional stride, what is convolution with a fractional stride? Anybody? What is a convolution with a fractional stride of 0.5? Is it just upsampling and then convolution? You upsample by a factor of 2, then you performed convolution with a stride of 1. And so trying to figure out the derivative rules, the backprop rules for this one can be very annoying. You can waste an entire day and eventually write buggy code. Whereas if I just decomposed it into this operation, upsample by 2, convolution with stride 1, it's trivial. We know how to backpropagate through this. We also know how to backpropagate through upsampling, all as well. In fact, if you go off on the web and begin looking at web pages and such like, blogs for convolution with strides greater than 1 or fractional strides are going to give you lots of very ugly pictures and algorithms and such like. There's absolutely no reason to understand or learn any of this. Once you know how to backprop through upsampling or downsampling, both of which are simple, and how you know how to backprop through convolution, there's nothing more to learn, right? And so for purposes of backprop, it's easiest to view this as upsampling followed by convolution. Backprop will first propagate derivatives through the convolution layer and then through the upsampling layer. Same thing, pooling and downsampling, right? Pooling is typically performed with a stride greater than 1. Pooling reduces the size of the map. So pooling was often just called a downsampling layer in the past, and often in the literature they'll just call pooling a downsampling layer, which is kind of a misnomer. It really isn't. It's really a combination of two operations, right? When you're pooling with a stride greater than 1, it's a combination of two operations, pooling with a stride 1 followed by downsampling. And so once again, it's easiest to view this as this combination of two operations, and you can backpropagate through each of the operations, and each of those backpropagations is very simple to perform. So did this make sense to all of you guys? Okay, and as always, so Rishabh, thinking of that for backpropagation, it's actually easier to implement it this way. If you want to go back and actually figure out the arithmetic to write the code so that you get the backpropagation for this upper picture directly, you will find it to be much more confusing. So simplification is the name of the game. We know how to understand it and we know how to implement it. But then code is always simpler, right? Remember what we said in the last class. if you were performing an affine, computing an affine map, you'd be going through the layers and then you'd be doing z plus equals w times y, right? And then you'd be, once the z values were computed, you put it through an activation function. And so we saw that if you wanted to perform back propagation, we just first went through all the indices in reverse order, then replace this operation by dy times f prime. If y is activation times of z, then dz was dy times the derivative of the activation. So also if zxy was incremented by wx prime y prime times y x plus x prime minus 1 y plus y prime minus 1, note the indices, then going back, the derivative for y at x plus x prime minus 1 y plus y prime minus 1 was simply incremented by wx prime y prime times dzxy, and the derivative for wx prime y prime was incremented by dzxy times y of x plus x prime minus 1 y plus y prime minus 1. So this was just a very simple modification of the code. You didn't need to understand the math. You didn't need to understand any concepts. You understood two simple rules. Then you have, z equals w times x. When you go to take the derivative back, then dy is dz times w, dw is dz times y, right? So this was when you had a stride of 1. But then if you have a stride greater than 1, in the forward pass, you'd be skipping with a stride. So guess what? In the code, you're going to use the same trick as here, except that when you're going back, you're going to be striding, going backwards. That's about it. So the stride going forward is going to give you the stride going backward. The code here is a little more complex because I'm showing you how we have to account for the striding, but that's about it, right? So code is always simpler. So also, if I'm max pooling with a stride, in the forward pass, I'll be looping with a stride. If I just change the thing going backwards, I'm keeping track of indices. So it turns out that in the max pooling case, you don't even have to worry about the fact that you had a stride when you were going backwards, because this index retains information about where the derivative came from. And so for mean pooling, again, when you loop backwards, instead of looping back, when you loop forward, you loop forward with a stride. When you loop backwards, you'll be looping backwards with a stride. That's about it. So always looking at things through the eyes of code can be much simpler than trying to figure out the math, but then you don't get a complete feel of what's going on. Here's your second poll. Okay, 5 seconds, guys. All right, let me end the poll. Okay, here's what you thought. And now here's my question for you. The backward pass of an upsampling layer is downsampling. True or false? The backward pass of downsampling is upsampling. True or false? Can you just use the upsampling layer as the backward pass of downsampling? And so how many of you think this is true and how many think it's false? Anybody who thinks it's false? Okay. That last one is false. Can somebody tell me why? Anybody? One guess? So it has to do with the edges, right? So when I'm doing a downsampling, If this were here, if I'm downsampling by 2, I'm going to be picking the first, the third, and the fifth layer, right? Looking at this guy doesn't tell me if there was a sixth layer here or not, does it? Does it tell me if there was a sixth layer here or not? So simply upsampling backwards by a factor of 2 can give me the wrong size, correct? If you are upsampling by a factor of 2, you'd just be getting only 5, whereas there could have been 6 on the input. It's just that the sixth layer got dropped, right? Yes or no? So here's the thing, Rishabh. If I had another layer over here, another column over here, would this column show up here, Rishabh? Okay. Now, if I were to upsample this thing backwards, what would the output size be? Here's the thing. Regardless of whether the input was with 5 or with 6, the output is still 3, right? So you have to store extra information about whether there was a sixth column here or not. So you can't just directly use the upsampling layer going backwards because of what happens at the edges. Conceptually, the backward propagation backprop for downsampling is upsampling, and the backprop for upsampling is downsampling. But because of what happens at the boundaries, we have to be a little more careful. Now, you can't just use one layer for the other. All right, so now we have seen how to compute the derivatives of the divergence with respect to every intermediate output and every parameter of every kind of operation. This can be embedded within gradient descent to learn the network. And so here's the story so far. The CNN is a supervised version of a computational model of mammalian vision. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer. And there should have been pooling layers that operate on groups of outputs from the convolutional layer. And this is a hangover. I should fix this. But this is how it's traditionally been considered. Again, pooling is distinct from downsampling. So I have a mistake on my slide. The parameters of the network can be learned through regular backpropagation. Max pooling layers must propagate derivatives only over the maximum element. Derivatives must sum over appropriate elements to account for the fact that the network is in fact a shared parameter network. So all of this is fine, okay, except for this one bug in my slides. But then let's look at other things that you guys have questioned me about, right? Convolutional neural networks are position or shift invariant. Regardless of whether the flower is here or whether the flower is here, the network will detect a flower. But then, if my flower rotated by say 20 degrees, will the network still detect a flower? Is it also rotation invariant? Yes, no. What do you guys think? Right, what if I scaled up the flower to this size? Is it scaling invariant? Or if I reflected it? It's only uh, invariant to translation, right? What if I also wanted to make it invariant to say rotation by 45 degrees? What would I have to do? Anyone? Augment. I can augment the data, but computationally, what's the more? Did we just augment the data to capture the flower in both positions? Or what did we do over here? We applied the same filter at this location and this location, right? So we made two copies of the filter, and we, which is the same as scanning, and applied them in different locations. And so Lewis is correct. Shift. So here's what shift invariant really meant. If you look at it from a different perspective, we shifted the filter to different locations to identify patterns, the same pattern at different locations. That's how we got shift invariance. If you want to have rotation invariance, instead of shifting the filter, you would rotate the filter, right? So if you want to also find patterns that are find patterns with an invariance to 45-degree rotations, then the filters would have to be rotated by 45 degrees. So you have one copy of the filter for the standard format, another copy of the filter for the rotated version, and each of these would be applied on your inputs. So each transformation of the filter is going to generate its own output channel. That makes sense? Did this make sense, guys? The transformation invariance, right? Okay, so if I rotate the filter by 45 degrees, it's now the pattern detection is invariant to 45-degree rotations. But will this also be invariant to, say, a 60-degree rotation? So if I also want to have 60-degree rotation invariance, what would I need to do? What would I need to do for 60-degree rotation invariance? Anyone? Rotate this thing by 60 degrees, right? So basically, I would have to enumerate all of the transformations that I would like invariance to. And so I want invariance to rotations by 45 degrees. I want invariance to, say, reflections. I want invariance to, say, rotations by 60 degrees. So for each filter, I'm going to make one copy of the filter with each one of the transformations that it can potentially, that I want invariance to, and then use all of those copies of the filter to generate the output, right? And what is the limitation of this approach? That's right, Duffin. So, so what is the limitation of this approach? Anyway, poor generalize. No, it's just that it has to do, you have to explicitly transform the filter for every one of the transformations that you want invariance to. If you want invariance to 45-degree rotation, there's a copy of the filter for 45 degrees. If you want invariance to 60-degree rotation, there's a copy of filter for 60 degrees. If you want invariance to all 360-degree rotations, you will have 360 copies of the filter. If I want invariance to scaling by a factor of 1.2, I'm going to have a copy of the filter at 1.2 scaling, right? If I want invariance to scaling by 1.2 and rotation by 45 degrees, there'd be a copy of it for that too. This is just not going to scale because the set of transformations you can handle is discrete and every one of them must be included. So here is your standard uh, convolution. You scanned at each location, you pulled out a segment of the input and you computed an inner product with a filter and applied an activation to it. If you want transform invariance, at each location, you would go through all of the enumerated transforms, which could be rotation, scalings, reflections, what have you. Transform the derivative, the filter, and then apply the transformed filter, which means that you're going to get as many channels over here, output channels, which as there are uh, transformation. So the indexing shows that if I have three filters and each filter is allowed to generate have 5 different transformations, I get 15 output channels. So this scales up very poorly and still doesn't generalize to newer transformations. But in any case, if you strictly want transformation invariance for any kind of transformation, this is how you would do it. And then again, this will also influence back propagation. So any filter is going to be transformed through all the various transformations in your list. When you compute derivatives, you're going to get derivatives for each of these transformations, and then you sum them all up to compute the derivative of the filter itself. We never do this, right? Uh, so Hannah, the answer is we don't do this because this just doesn't scale. So what do you think we actually do? Anybody? What do you think we actually do? We just augment the training data. We think of all of the different ways in which you can modify the training data and still have it recognized, and apply the transformations to the training data and just train a bigger model and hope it learns the generalization. And that actually works, whereas although this is mathematically the correct thing to do, this is not a scalable or an implementable solution. So everybody with me so far? Yes, no? Okay. And so adding to the lessons, the models can be easily modified to include invariants to other transformations, but this can be computationally painful, right? Here's another thing. All the model does is to tell you if there is a flower in the picture. Does it tell you where the model is, the flower is in the picture? No, right? Because we scanned and then we passed the entire collection of outputs through effectively an OR, right? And so you can detect there's a flower in the input, but you can't detect the location of the flower. Where is the information about the location of the flower? Anyone? Where is the information about the location of the flower? Remember, so what we did was scan, right? And so when you scanned it, you got this map of outputs. This guy was flattened and became a long flat vector. And this was put through a softmax or an MLP, basically some decision, right? And because we combined the decision, all of these guys, maybe you put them through an OR, by the time you got to the output over here, you only had information about whether there was a flower or not, but you didn't have information about where the flower was, right? Where is the element about where the flower was? Anybody want to answer me? I have one answer. What about the rest of you guys? This map here, that has information about where the flower is, correct? Yes or no? It's just that we ORed all of them. That makes sense, right? Which means this flattened vector here, this has information about where the flower is, right? Yes, no? That makes sense to you guys. And so if I want to find the location of the flower, I'd have to use the final flattened vector before it went into the decision layer. And so that's basically what we do when we want to find the locations of objects. This final flattened layer, you can just put it through your standard decision layer to decide if the class is present or not. But then you can pass it through a second network, which will tell you the coordinates of your object, typically represented in the nature of a bounding box. So when you train the network, you're actually going to be using, the network will have to be trained to actually extract this information. And so your training data are going to have two kinds of labels. One is the class output itself. The second is the position information. And that position information is used along with either an intersection over union loss or an L2 loss, and to train the parameters of the network that derives the bounding box from the final representation. So you'd have two losses, and you're going to be training the network using a combination of two losses. Does this make sense? Yes, no? Okay. And same thing, right? You must have seen images, examples of this kind of stick diagram where it can actually draw your skeleton for you. It's kind of scary, right? It turns out you can use the same mechanism, except that instead of using this representation to find a bounding box for the person in the image, you can find the location of the various joints, the XY coordinates of all 14 joints. And then if you connect them up, you're going to get a skeleton-like picture. This is used for pose estimation and such like. If those of you who had, if any of you had visited CMU, say 6 years ago, just before COVID, there used to be a big screen at the end of the corridor that connected Hillman to gates to the Newell Simon building. And on that corridor, as you walk down the corridor, it would draw your skeleton for you live. It was very spooky, but did a fantastic job. And we had that for a few years. How did that work? Basically, this is the idea. And this kind of mechanism for drawing the joints and the stick diagram for the people in an image is used in many applications. What it really does is to identify the locations of these joints, and that's done using this mechanism over here. Of course, you will need training data in which these joint positions are tagged so that you can train the model properly. This makes sense? Yes? Okay. I have 2 yeses. And let me. This one has 3 questions in it, guys. Okay, 15 seconds. All right, let me stop this. Okay, first statement, true or false? Second one, true or false? Third one, true or false? Right, all 3 are true. That's enough, right? So basic ideas. We got through all of the basic ideas for convolutional neural networks. We'll go through some model variations, things like very deep networks. How can I make the network 100 or more layers deep? This is a ResNet. And something called depth-wise convolutions. Let's see what they are. Now for this one, it turns out that for very deep networks, it turns out that if you keep adding more and more convolutional layers, as you go back and perform back propagation through the network, your derivatives will become unstable and vanish. And so it's hard to train the network. So we use a formalism called ResNet, which I'll briefly allude to. The one that's more interesting is depth-wise convolutions, where we just take the whole concept of parameter sharing one step further. And so for that reason alone, it's interesting because it shows us how parameter sharing can be used to increase efficiency by extending it. Now, here is a standard convolution. You'd have an input with many channels. You have a filter, and the filter has a phase, but the filter has as many channels as the number of input channels. Then, when you convolve the filter with the inputs, one way to think about it is that each phase of the filter convolves the corresponding phase of the input. Each channel of the filter convolves the corresponding channel of the input. And so in the first step, you're going to get as many channels as the input itself, where each of these is basically the convolution of one channel of the input with the corresponding channel of the filter. And then subsequently, all of these guys are just flattened, summed up to give you the final sum of the output of the convolution. So is this making sense? This is also just is the same standard convolution operation. And presenting the way we presented it typically initially was that at each point I did an instant sum and you got a single output. But then I can break it up into 2 steps, where each channel of the filter convolves the corresponding input channel to give you the convolution outputs channel wise, and then you sum them up to get the final output. Is this making sense? Here. Yes, no. So I'd like to see a few more yeses. Yes, 4, 5, maybe 10. It's nice to know that at least 10% of the class got it. Okay. So this is easy, right? And so if I have many different filters, what would happen is that for each filter, each channel of the filter would convolve the corresponding channel of the input. And so computation wise, what is happening is that you'd compute all of these guys. For filter 1, every channel of the filter would convolve the corresponding input channel, and you'd get a bunch of channels. For filter 2, again, same thing. Every channel of the filter would convolve uh, the corresponding channel of the input, and you'd get a bunch of convolved channels. Filter 3 would get a bunch of convolved channels, and all of these guys would be different because the filters are different. And then you sum all of these up to get the final output of the first filter. You sum these guys up to get the final output of the second filter. You sum these guys up to get the final output of the third filter, right? The key here is the collection of convolved channels that we get is different for each filter. And those are what are summed up. Now I can take the concept of uh, parameter sharing one step further by saying that I have one single multi-channel kind of filter where each channel of the filter convolves the corresponding channel of the input. And so now I get as many convolved channels as the input, but now instead of just directly summing them up, I will do a weighted sum, and different weighted sums will give me different outputs. So instead of having 3 filters over here, I have 3 filters, each with its own convolution. I have one set of convolutions, and the differences between the filters is simply the weights with which these things are combined. Do you see how this works? Yes or no? I see one yes. What about the rest of you guys? Did this make sense? 2 yeses, 3, 4. Can I get at least a dozen right? Okay. It captures, yes, Stacy, it will capture less information than the normal one, but you get a lot of computational benefits, right? And so here is what would happen. In terms of parameters, if I had n filters, or if I had m filters, n filters, and there were m input channels, and each filter was k cross k, then each filter is going to have k cross k times m, so m k squared parameters. There are n filters, so the total number of parameters is going to be n m k squared. Whereas here, I just have, since this one is common to all of those, so the filter components that go from the input channels to this collection of convolved channels is just going to be one set of m k cross k parameters. And subsequently, these guys are combined using different weightings to generate the output channels. So in the stage 1, I have m independent k cross k 2D filters. In stage 2, I have n independent m cross 1 cross 1 1D filters. And so the total number of parameters is going to be mk squared plus n times m. So as you can see, the number of parameters can be orders of magnitudes fewer in this second case. Also, in terms of computation, here in this case, in this case, every one of those is these is going to be performing a convolution. So you would have n times m convolutions, whereas here you perform the convolutions only once, so you have only m convolutions. So you get a massive reduction in the number of parameters and a massive reduction in the number of computations as well. So this is the so so these guys, they're all going to be weights, right? It's just that this is done once. So here you have k squared times m. That's the number of parameters that you would have at this stage. And then over here, you have m of these guys. So the weights, you have m weights for each output channel. So you have n times m weights for the second stage. Did that clarify your doubt? For conventional, here's what you'd have, right? For conventional, you have k squared times m for every one of the filters. And so each of these is independent. And each of these is going to perform a different convolution. Right? So you get a massive reduction in parameters. Here's your final poll for the day. This is called depth-wise convolutions. Okay, 10 seconds. All right. This is what you guys thought. So Daisy, for depth-wise, you would have each of these guys. This set of convolved outputs is the same for all the outputs channels. The weights with which you'd be summing them up is going to be different for each output channel. Right. And so the answer is filters and depth-wise convolutions convolve all the input channels simultaneously and sub the results. They don't, right? They actually convolve each channel independently and keep them as separate. And the manner in which they are combined is what is different from output channel to output channel. But they require far fewer parameters and they require far lesser computation. And so adding to our list of lessons, we can make predictions related to position and arrangement of the target object through multitask learning. And variations of the basic model exist to obtain greater parameter efficiency, greater ability to compute derivatives, etc. Now, what do the filters learn, right? If when you have a distributed scan, the first level filters look at a small region of the input. The second level filters look at regions of these guys, and so they end up looking at a larger region of the input. Third level filters look at regions of these guys, and so they end up looking at a still larger region of the input. So what kind of patterns do each of these guys capture, right? So in the case of the first level filters, to see what pattern a filter captures, you just need to look at the weights, because you're basically performing an inner product between the weights and the corresponding region of the input. So the weights will directly tell you what the filter captures. But for the second level filters, it's never, you can have all kinds of combinations of these guys. So it's never immediately apparent what triggered this particular neuron, this filter. And so you'd have to, when it's triggered, you'd have to actually perform back propagation and perturb the input to find out which regions of the input actually cause this filter to fire. But you can do this analysis, right? And here's the kind of here's what they found in this example. It's a network which has been trained for recognizing different classes. And observe something. These are the activations of the first layer filters. What do these look like? These are the patterns they respond to. What do they look like? The first layer filters. Anyone? Oriented lines, right? What does this remind us of? Did we encounter this earlier in the course? S cells. Basically, it turns out that when you train a convolutional neural network, it ends up capturing the kinds of patterns that your mammalian vision actually captures itself. Just like your human brain or the mammalian brain responds primarily at the first level to oriented patterns, so does your convolutional network. So that's, the fact that this computational model ends up mimicking the brain so well is pretty shocking, at least to me, right? Now, when the input presented as faces, they find that the next layer, neurons, actually end up responding to things like eyes, portions of noses, and so on. And deeper in the network, the different neurons respond to actual face-like patterns. On the other hand, when you have cars at the input, the intermediate layers correspond to components of cars. The deeper layers actually respond to entire car-like images. Here's the same thing for elephants. Intermediate layers respond to parts of elephants. The deeper layers capture entire elephants. So you can see that just like in the mammalian vision, even convolutional networks build up the patterns that they're responding to through the layers of the network. I don't know about you. I find that this computational model basically learned something very similar to mammalian vision to be quite fascinating. Now, when you train it, you have standard convergence issues. So you need Adam or other momentum style algorithms. You need batch norm. The number of parameters can become very large. So you will often run into insufficient training data to train well. So we tend to use a lot of data augmentation where we modify our input uh, by rotation, say uniformly chosen random angle between 0 and 360 degrees in the case of images. You can take the same image and shift it around, translate it a bit, you can scale them, you can flip them, you can perform other operations that don't actually change the class and use those as augmentations. And this is done a whole lot when you train these models. Anyway, just coming to the end, CNNs are one of the most frequently used formalisms today. They're used everywhere, not just for images, but used in speech, audio, on spectrograms. They're also used in text processing. Now, before I continue, uh, actually, Karpati has a very nice visualization for how these things work layer by layer on his webpage. If it's still up, you guys should check it out. So, just a little bit of history. So, where did all of this come from? The very first convolutional layer neural network was by Jan LeCun. That's basically what he won his Turing Award for. So, here's what his model looked like. He was analyzing digits. At the very first layer, he had six 5x5 filters. Then he followed it by a bunch of pooling layers with a stride of 2. Then he had 16 5x5 filters which operated on this, followed by pooling, and then finally an MLP. Now, do you remember why we have to increase the number of number of channels as we go through the network? Anybody remember that? Why do we have to increase the number of channels? To not lose info, because each channel becomes smaller. When the channel becomes smaller, you need more of them. Otherwise, the information is going to be lost. And so this was our first big success for convnets. But the real, where neural networks really took off, this was 2012, was when it was shown that they could take a SOTA task and outperform everything on the planet by a huge margin. And the task was ImageNet classification, where you have millions of images and thousands of categories. And so the original work was using 1.2 million images in 1,000 categories. And these guys, Hinton and Ilya Sutskever and Alex Krzyzewski, they showed in this NeurIPS 2012 paper that they could get really, really good performance on this data. And this was the first time that we were using huge models to analyze what seemed like a limited amount of data. They had a neural network with 60 million parameters. They had 650,000 neurons. They had to distribute it over 2 GPUs back in the day, and the network was so big that they couldn't even actually draw the entire picture in their paper. This figure here is how it appeared in the paper. The upper portion of the figure got trimmed off. Some details of their model, fairly complex. But then here's what they got: 650 K neurons, 60 million parameters, and 630 million connections. Now this is greater than this because parameters are shared. During testing, they didn't just present a single image, they cropped it in many different ways, shifted it, and presented the same image many different times, and then voted over the lot. They introduced a few important things that we still use. Prior to their work, convolutional neural networks still used sigmoidal activations, going back to Jan LeCun. They showed that you're much better off using ReLUs. They introduced dropout in the neural network. They used and a bunch of other factors, other techniques. This is the key piece. Prior to their paper, the best top 5 performance on ImageNet was about 25% error. Their network jumped all the way from 25% to 18.2% if they used a single network. If they trained 7 different networks and voted over them, the error went from 25% all the way down to 15.5%. So in a single step, they reduced the error on this task by 40%. That's when the world woke up and said, hey, here's something that looks really, really promising. Let's go with it. And so convolutional networks and more generally neural networks took off. So here again are the receptor fields of their first layer neurons, and you can see once again that it seems to capture the kinds of patterns that mammalian vision does, right? They also showed that it learns very useful representations. It learns features. Now, first, here are some classification results. These are successful ones: mite, container ship, motor scooter, leopard. But even when it made mistakes, often the mistakes were very understandable. This is classified as a grill in the database, but the model recognized it as a convertible, and I don't blame it, right? So according to the database, this is a cherry, but the model recognized the Dalmatian. Again, I don't blame it, right? Uh, and here's the more interesting thing. They would take the final representation just before the classification layer. They would compute it for the entire database, and then you take a test example, compute the representation, and pull out other instances from the database that were similar to it. And they found that when you queried using the image of a flower, the other things it pulled up were flowers. For an elephant, it pulled up elephants. Basically, the representations it learned were also useful for retrieval. This was another huge first. We use it all the time. This was the first time we realized that these models, when properly learned, derive representations that actually capture the semantics of the underlying data. And that's central to everything we do today. Then, of course, there was a lot of there were lots of engineering advances immediately after that. Zeiler and Fergus changed some parameters, reduced the error from 15.4 to 14.8. These guys, VGGNet, they trained a network with 140 million parameters on just 1 million images. And they ran thousands of experiments, and eventually managed to bring the error down from 14% to about 7%. Google then had to want to be left behind, so they came up with a very ugly, hideous architecture called Inception, which brought that down to 6.7. And then ResNet came by, where ResNet was this model which allowed you to have hundreds or even thousands of layers. And the way they did it was, instead of transforming the input completely, they computed corrections to the input. So the network would compute some output and add it back to the input. So now every layer effectively corrects the input. And once you do that, you can string hundreds of layers together. So with 150 layers, they brought the error down to about 3.5%. Again, this is all within a year. The error has gone down from 25% to 3.5, right? Some examples for ResNet. DenseNet guys, they said, why does this have to be sequential? Why can't this layer connect directly to this? And so they created a network where every layer fed to every subsequent layer, and the error went down further. And at some point, the changes were coming in so fast that if you blinked, you went away for coffee and came back, there would be an improvement in the error rate on ImageNet. So, uh, ImageNet, the convolutional uh, neural networks are important not merely for what they do, but also what they stand for historically. CNNs were the first time back in 1989 when the world sat up and took notice that you can do shift invariant pattern recognition and that most problems in the world are shift invariant. But then things went quiescent for, 3 decades, and you know, or two and a half decades. And then they came right back and they showed that the same thing can now be used to obtain huge improvements on state of the art tasks. And then the improvements that Hinton and co came up with introduced many new principles that we still use today. So CNNs are actually a key step in the progression to what we currently have for AI. And you can still find daily updates on archive. They're used for everything from speech rec to language processing to what have you. So I'll stop right here. Here's a CNN for speech rec. And this is the last of our lectures, series of lectures on convolutional networks. From the next week on, we will be talking about recurrent neural networks. I will pause to take any questions. Do you have any questions?